Hello, I'm Bo-Kyung Lee from Dongguk University DTM Lab. The paper I will review is Evaluation and Identification of Potential High-Value Patent in the Field of Integrated Circuits using a multidimensional patent indicators, pre-screening strategies, and machine learning approaches. First, this is a bibliographic information of the paper. I reviewed this paper because I wanted to select indicators that can be used to predict the growth of technology when conducting individual research. This paper aimed to identify automatic evaluation and identification method using a machine learning approach. Considering economic and technical importance of high-value patent and patent evaluation method. The contents are the same as the structure of the paper. This is the introduction. The economic and technical value of a patented invention can influence subsequent technological development and effective patent evaluation, and the identification of high-value patents can provide decision makers with information on technological investment and patent applications. Therefore, evaluating the value of patent is a topic of interest to both academics and practitioners. In addition, high-value patents have high economic, technical, legal, competitive, strategic, and scientific value. Therefore, using a wide range of indicators to caption patent value across various dimensions can better reflect the overall value of a patent. Next is the related work. Extensive efforts have been made to explore indicators for evaluating patent value, and machine learning has emerged as a patent value evaluation and identification tool for processing, analyzing, and assess large volume of patents. This model can automate the patent evaluation process to replace the entire or particular expert evaluation that are traditionally conducted manually. This following is an explanation of patent value indicators. In this study, high-value patents are evaluated and identified using a portfolio approach that include indicators for high legal, technical, competitive, and scientific dimensions. Fourth, the legal value. Legal dimension indicators include patent claims and family size. Claims are the fundamental unit for measuring the creativity of a patent. The claims of a patent involve the legal definition of the invention and grant exclusive rights to the invention protected by law. The number of claims in a patent indicates the scope and breadth of legal protection. Therefore, a greater the number of claims, the broad the scope of legal protection, making the patent more resilient and longer-lasting. The patent family size refers to a total number of jurisdictions where patent protection is sought for the same invention and reflects a company's innovation strategies, patent portfolio, and confidence in the return on investment in the patent. In this context, the larger the number of countries in which a patent is granted, the greater the patent family size. Next is the technological value. Technological dimension indicators include the first, citation speed and classification scope. The probability of a patent being cited is highest at the younger patent age, and important patents often receive more citations for more quickly. The earlier a patent is first cited, the more citation it will receive thereafter, and its importance increases. Therefore, the faster the first citation lasts, the greater the technical value of the patent. The number of IPC categories, such as the classification scope, measures the technical breadth. An increase in IPC categories indicates that the patent invention spans multiple technical fields and has various technical. Therefore, the number of IPC classes assigned to a patent reflects the patent's significance. Next is the competitiveness value. Competitiveness dimension indicators include the forward citation, extended patent family size, inventor team size, and number of patent holders. Forward citation represents the citations a patent received and assess its innovation, economics, and market value. The higher the technical quality of a patent, the more inventions are built upon it, increasing the patent exclusivity value. Therefore, the more poor citants a patent receives, the greater its contribution to subsequent inventions and its value. The size of an extended patent family indicates the number of subsequent inventions built upon a specific patent technology. The larger the size, the more comprehensive the scope of application of the patent technology, and the stronger the protection of rights and competitive advantage. The size of an extended patent family demonstrated a company's ability to integrate and encompass industry, market, and regulatory factors covering temporal, geographical, technical and product dimensions to develop a patent portfolio. Therefore, the extended patent family size of a technology reflects its competitiveness. The size of the inventor team is consistently corrected with patent value and technological usefulness. As the inventor team size increases, the patent research and develop knowledge base becomes stronger, and the likelihood of the invention being highly competitive increases. The number of patent holders reflects the allocation of resources to the invention. The greater the number of patent holders, the more investment, maintenance, and operational status are indicated, which continuously realize the patent value. Next is the scientific value. Scientific dimension indicators include the length of patent instruction document, non-patent references, and patent references. The patent specification includes technical descriptions, specifications, claims, and other information. The length of the patent specification presents the technical scope, details, and achievements of the patent. Therefore, there is a positive correlation between patent value and the length of the specification. Patents can be based on new scientific knowledge, and scientific papers serve as a source of new knowledge and evidence that supports inventions based on that knowledge. Patent that directly relies on scientific literature can better reflect a closer scientific connection compared to patents that are based solely on existing technologies. Backward citation refer to the references of existing technologies derived from a patented technology, and they are used to assess the novelty of the patent invention while reflecting the knowledge linkage across different technological fields. The greater the number of backward citations, the stronger the technological foundation of the invention, which tends to indicate higher market value. Next is the methodology. This paper presents the methodology to evaluate it and identify high-value patent. The left column shows the theoretical foundation for selecting value indicators and building machine learning models. The right column displays the key activities related to the process. First, the construction of the patent database. The IC industry is involved in nearly all modern technologies such as 5G, AI, quantum computing, IoT, which results in a large number of high-value patents. Therefore, this study tested the proposed method in the IC field. Next, multiple patent indicator data is obtained. The number of patent claims, the size of the extended patent family, the number of inventor, the number of patent owner, the number of specification page, and the frequency of backward citation all calculated. Duplicate data is removed, and the quality of indexed data is ensured by showing deviations and stability of abnormal patent data through statistical analysis. Subsequently, the patent data is used to evaluate and identify patent value. By pre-evaluating patent value using the patent value indicators described earlier, the multifaceted characteristics of high-value patent are reflected. The pre-review stage lays the foundation for using machine learning to automatically identify and classify high-value patent. Next is machine learning identification method for potential high-value patents. Various machine learning models have strengths and weaknesses in processing patents data and identifying high-value patents. Therefore, this study selected naive-Bayes, logistic regression, random forest, support vector machine, and artificial neural network for comparison. Naive-Bayes model used the following equation to identify high-value patents through maximum likelihood learning in order to obtain the final classification of the sample. In this case, maximum likelihood estimation refers to a statistical method for finding the parameter values that best explain the given data. Logistic regression uses the logistic function to map the output values to 0, 1 and set a threshold to determine the classification of the sample. It combines the standard logistic sigmoid function with the regression model and assumes that the data follows a binary 0 to 1 distribution to model the probability of the given sample. Random forest constructs multiple cause decision trees to perform classification tasks by selecting features based on the Gini index. The smaller the Gini index, the higher the feature pretty of each child node, and the lower the data uncertainty. Support vector machines have two types, linear and nonlinear. Linear SVM is applied when the data can be perfectly separated linearly and when the sample space is nonlinear separable. A corner function is introduced to map the samples to a higher dimensional feature space. The artificial neural network used a 3-layer neural network structure with a single hidden layer consisting of n neurons. Afterwards, to improve the learning and generalization capability of the classification models, The parameter values of each model are explored using methods such as network search. The dataset is divided using the k-fold cross-validation method, and model performance is measured using metrics such as accuracy, precision, and recall. Finally, the performance of the classifier is visualized through the area on the ROC curve. Next is the implementation page. First, it is the multidimensional evaluation and pre-screening of high-value patents. This table presents the descriptive statistics of 11 patent indicators, including maximum minimum values, mean standard deviation, evaluation number, and data dispersion range. In this case, the evaluation number column and the numerical performance column represents the number of selected high-value patent samples and their numerical performance for each indicator. Next is the construction of training and test set for machine learning recognition. Since the distribution of high-value patent and other patent in the entire dataset is 28% and 72%, respectively, using pure random sampling could lead to significant deviations in the experimental result. Therefore, stratified sampling is used to extract patent with the same proportion from the other patent, ensuring uniformly distributed training and testing set. The data for each indicator is standard, and the attributes of various samples are scaled to the range of 0 to 1, forming a standard value feature vector space for integrated circuit patent. Below is the model training and optimization process. Manual parameter tuning, network parameter tuning, and optimization of the parameter learning curves were combined to pursue optimal performance on the model's dataset. The table summarized the specific optimization methods and optimal parameter for each model. Next is the result. First, the prediction of potential high-value patent based on the pre-screening multidimensional patent indicators. This table summarizes the performance of 5 classifiers in terms of accuracy, precision, recall, F1 score, and AUC based on the pre-screening multidimensional patent indicators. It can be observed that random forest achieved the best overall result. Next is the characteristic of value indicators of potential high-value patent. This table shows the average difference between high-value patent, the entire sample, high-value patent, and unsighted patent. The larger the difference between the average of high-value patents and the patent indicators of the entire sample, the more pronounced the legal technical, competitive, and scientific value of high-value patent. In addition, the average of the patent indicators is sufficiently different, so the model tested in the study is able to distinguish high-value patents from the other patents. This table represents the high-value patent identified in the study. Next is conclusion and implications. The methodology proposed in this study follow a holistic approach and can be applied to research on patent value estimation in other technical fields. Furthermore, this study demonstrates that the first science citation rate metric is beneficial and valuable for value estimation. However, it should be noted that the performance of the machine learning model may vary if other value metrics are used in constructing the model of if the model is applied to different fields. Additionally, this paper collected patent information from the DOINT database, meaning that the selection of value metrics was constrained by the data provided by the database.